Hello, everybody. Thanks for the invitation. Hello, Laura. Yeah, of course, this is your master's project. Thanks for sharing your slides. Okay, so rapid climate change is not new. It occurred repeatedly during the Quaternary. Oh, by the way, this is the follow-up of my last year's talk at the IRN. So those of you who were there, yeah, you were expecting this, right? All right. So, okay. So from these climate change that occurred during the Quaternary, we are able to better, have insights about species responses to global climate change, which can be grouped into migration, meaning range shift, extinction, or adaptation of populations. With ongoing climate change in high latitudes, in our high latitudes, we expect about twice to maybe 4 times the global climate change average. So as we just saw, some authors suggest or fear that migration might be too slow to track global climate change velocity. This is based on the discrepancy between expected global change speed and the species dispersal capacity. But it assumes that species are fixed in their dispersal capacity. However, marginal populations located at the edge of species range should readily experience novel environments and thus evolutionary pressures, which could trigger amplified response to global change. And one thing that is repeatedly ignored is the potential interplay between migration and evolution. For instance, increased adaptation for dispersal speed during range expansion. In the northern hemisphere, we find the ecotone between forest and tundra. This is where we find the Arctic and the alpine tree lines. We all know these areas, except maybe Matt. So this is where we find the harshest climate condition for trees, especially during the Little Ice Age, where we had limited tree growth and regeneration. Of course, since the Little Ice Age, as well as ongoing anthropogenic global warming, we see recent expansion into the tundra, so a range shift. So what do we mean by expansion? In fact, it is the colonization of some population beyond the species range limit. So it reflects the expansion, or this is due to some in fact, the expansion potential reflects the dispersal capacity, the seed viability, and the establishment and survival of seedlings and saplings. So what we see is isolated populations at the expansion front, which come from long-distance dispersal followed by local densification. And when you go at a tree line, a latitudinal tree line, it is obvious that this is the process. If it's not, well, let's not go there. Okay, so since I'd say over the last decade, a theoretical eco-evolutionary model emerged called the spatial sorting that could actually change the paradigm. So in a nutshell, fast dispersing individuals at the expansion front will inevitably breed with each other, simply because any slow dispersing individuals will have been left behind, right? So as migration proceeds, successive generations should accumulate novel phenotypes adept at rapid dispersal at the expansion front. This should be exponential. So, and what is interesting is that the underlying alleles, the alleles that basically code for those phenotypes, surf on the expansion front, and natural selection is virtually ineffective. So in fact, it does not require the gene involved into those phenotypes to affect an organism's survival or reproduction. this is really contrasting with what we should find in the range core, where natural selection should work to optimize individual fitness. For trees, wing loading is a good proxy for dispersal capacity. Wing loading is a ratio of the seed mass to the wing area. So lower wing loading means higher dispersal capacity, but it also implies less resources to the seed. So under the spatial sorting model, there should be a trade-off between dispersal capacity and reproduction. So this incurs a fitness cost to the spatial sorting model. Now we're gonna assess this with white spruce, which is a transcontinental boreal conifer species. And in Eastern North America, it's mostly found in the southern boreal forest, where it's a companion species in the balsam fir dominated forest, which is a fire intolerant forest. White spruce is also found as forms the altitudinal tree line in the Monts Groulx in the boreal forest and the McGerrigle Mountains in the Gaspé Peninsula. What we see is usually how do we say this word?
Montane.
Montane. All right. Montana, whatever. Montane. Right. I just looked at it this morning. I was like, okay, Google, tell me how to say it, and just I forgot it. So Matt, if there's a problem, just, okay. So montane forest, where we find spruces, both species, as well as balsam fir. And then as we go up in elevation, we find the subalpine tree line, where it's mostly open white spruce forest. And then as we go still upper in elevation, we finally end up with white spruce chromholds in the alpine tundra. All right, so we assume that subalpine stands are currently undergoing expansion in the alpine tundra. So the objective here is to test the spatial sorting model with empirical data and its fitness cost by assessing white spruce seed dispersal capacity and seed viability along the altitudinal gradient. Fairly simple. We expect lower wing loading, so higher dispersal capacity at tree line and tundra sites, and lower seed viability in sites with higher dispersal capacity. So the study area is, as I said, the Monts Groulx. We have two mountains there that we studied, Geoffrey Provencher, and the Monts McGerrigle in the Gaspé Peninsula, where we also studied two mountains. And as say control site of balsam fir forest at low elevation, we have balsam fir forest in Parc National du Bic, thereafter called Bic. Okay, some pretty pictures because we all like pretty pictures. So these are montane forest, so balsam fir forest, subalpine tree line, white spruce subalpine tree line, and alpine tundra, right? Sampling, straightforward. One site, control site in the Bic, in the balsam fir forest. We have 4 mountains, 2 in each regions, where we study the montane. I'd never be able to say this word. Okay, so montane forest, tree line forest, and the alpine tundra. We studied sampled 15 trees per site, 10 cones per tree, and 10 seeds per cone, for a total above 7,000 seeds, on which we looked at wing area, seed mass, and we conducted germination tests. We also took 5 mineral soil samples to assess charcoal presence, witnessing fires. Yes, I'll show a picture of that. A movie. Results, because we all like results, right? So here we see wing loading. Remember, higher wing loading means less dispersal capacity, right? Of all our sites. Okay, so here's the Bic, so our control site of the balsam fir forest, McGerrigle Mountains in the Gaspésie, and the Groulx Mountains. and each color represents a different elevation. So basically, main results, the wing loading of control and montane forest. In fact, the wing loading is highest in the Bic, so in the Balsam fir forest, and lower in the Groulx region, and lowest in the McGerrigle mountain. Now, our most interesting result, wing loading in the tundra and tree line, it's higher in the McGerrigle compared to the Groulx mountain. We found no altitudinal difference in the McGerrigle, but we saw altitudinal differences in the Groulx mountain, whereas mountain sites have higher wing loading compared to tree line, compared to tundra, right? So just to see it another way, in the McGerrigle, so in the Gaspésie Peninsula, for a given wing area, mass does not vary with elevation. So the three slopes overlap. Whereas in the Groulx mountain, for a given wing area, seed mass is higher in the montane forest compared to the tree line and tundra, which do not significantly differ from one another. Now, germination probability is completely invariable in the McGerrigle mountains, whereas it significantly decreases with elevation in the Groulx mountain. And overall, germination probability is 25% in the McGerrigle, which is also the highest value at lower elevation in the Groulx mountain. Overall sites, there is a decrease of germination probability with elevation, and it reaches 50% within the balsam fir forest in the Bic area. As for charcoal, well, basically easy results. No charcoal was found in the McGerrigle, and a lot of charcoal was found at all sites in the Groulx mountain, right? So no fire and fire. Now let's interpret this together. In the Groulx mountain, where there's fire, wing loading is lower at the tundra and tree line. So this is coherent with an imprint of spatial sorting. In the Groulx, tundra, and tree line sites, we found lighter seeds, and correspondingly, we found lower germination probability. In the Monts Groulx, there is recent fire. We date some charcoal and dates back to 300 to 600 years ago. So these stands are young, and they are recent colonization is still ongoing. So in the Groulx mountains, we have dynamic stands where expansion process is still ongoing, spatial sorting seems to be occurring, and natural selection is still ineffective. In the McGerrigle, wing loading does not vary with elevation, so there is no signature of spatial sorting. Seed mass does not vary with elevation, so germination probability is also invariable. There's no fire in the McGerrigle mountains. Stands date back multiple generations, at least 7,000 years before present. So we have equilibrium stands where spatial sorting is no longer acting, but natural selection had multiple generations to optimize the trade-off between dispersal and regeneration. Now our control site, the Bic area, the balsam fir forest per se, is where we found the highest wing loading. So there's low dispersal capacity within the balsam fir forest, which is most likely where we gathered some samples to assess migration possibility or dispersal capacity of this species. So there's also heavier seeds in this area, which is coherent with the highest germination probability we found. So in the core of the range, in the balsam fir forest, natural selection optimized germination over dispersal. So trees from range core stands are basically poor indicators of the dispersal potential of a given species because natural population is maximizing regeneration over dispersal. And my main conclusion, I have only one conclusion, it's that spatial sorting implies that trees can actually migrate rapidly at the expansion front, which is where it actually matters, right? And boom. Yeah, done.
One question. You say that for the one site we have a recent fire. This one where we go back with charcoal 500 years ago, and you say that it's a recent fire, and you don't have many generation in order to make this adaptation to.
Yeah.
And but do you think that this fire restart totally the system because it could be just little fire that did not burn all the forest, and we can have generation that is only present during this fire. Even if you have fire, but this fire does not restart totally the system. The first question, and the second one about the balsam fir forest. You also make charcoal insert to see if you have fire in this one.
Not sure.
Not sure.
Not sure. If we do, they're not analyzed yet.
Okay. Okay.
But regarding the you mean if they're crown fire or surface fire? Well, yeah.
Yeah.
But it's hard to tell. But
Yeah,
it's hard to tell. But it's it's not pine, so I kind of assume it's spruce and replace. Huh?
You suppose it's not crown fire?
Yeah. And the forests are fairly young, to be honest.
It's young.
Yeah.
Okay.
Well, young, not that young, but trees are. It's.
Yeah. Okay.
Yes.
I had a question that when you talk about this spatial sorting, what you presented was the same thing where you go actually at spatial sorting between tundra and forest. But then, when we talk about lots of these migration-related issues, we are actually talking about southern trees expanding into mid-latitude or boreal forest.
Yeah.
Where actually competition may matter actually inside there. So at the tundra line, you could think that competition perhaps doesn't matter very much. But when you have sugar maple going into black spruce or balsam fir forests, you would have competition which matters.
Yeah. I'm talking about the expansion of the tree line, the range shift. Or yeah.
Biome shift.
Yeah, you could say of course maple. Well, yeah, there will be other if there's other. There could be other processes as well. This is kind of what happens when you move from it assumes no competitions. You're right.
We have a last question online from Fabio.
Yeah. Hi, Fabio.
Salut, Guillaume. Do you hear me?
Yeah.
Okay, perfect. So thank you for the presentation. It was very interesting. But I was asking because you present this wind loading, which is a ratio between the mass of the grain and the wing size. And did you check if, for example, it's only the mass of the grain that vary and that is dependent only because of the limitation due to environmental condition in some tundra site?
Maybe we did, but I haven't looked at these results yet. It's these are the student working on this, Laura. She's done she sent me the work, and of course we'll look at each variable individually. You're right to point that out. This is still something we got to do, but of course we have the data for each variable individually.
Yeah, just because it can change a little bit the interpretation.
Yeah, you're right.
Okay, thank you, Guillaume.
Thank you.
Thanks.